Good news, gang. We've got all the components in place now to be able to look at and understand how we define EIRP, the effective isotropic radiated power, the oomph of the signal as it leaves an antenna. So let's take a look here, gang. What do we got? What are we putting together here? 3 key pieces of information. Number 1, we're going to start off with an access point. That access point is going to have a certain amount of power measured in dBm that it's going to use to send out its signal, right? So how much does it start off with? Well, let's say we've got an access point with 17 dBm. Then there's a certain amount of decibels of loss, especially when we've got to go to an external cable here. So here's a parabolic antenna, and we're designed to go kilometers in distance, good stuff. Typically going to have a cable, right? But that's not, parabolic antennas are not plugged directly into the access point. So we measure that in terms of cable loss, and let's say that for every 100 meters, you lose 12 dB. All right, that might be the scenario that you're dealing with, right? So that's how the cable's rated. Now, the fact is you're only going 25 meters. All right, so a quarter of the distance, a quarter the decibels of loss. So that means we're just down to 3 dB of loss, -3. That's a negative, remember. Cables are not helping your signal, they're only hurting it. But then the antenna itself is a directional antenna designed to boost that signal a specific direction to a certain amount of decibels. This guy's got 28 dBi in terms of its antenna strength, what it's providing to that situation. So when you put all that together, the 17 plus the 28 minus the 3, what do you get? 42 dBm, all right? So the final measurement is considered dBm, decibels measured against watts. That is our rating of EIRP for this specific scenario. Now, again, we may also want to know that in terms of watts. You do remember how to convert decibels to watts, don't you? 42, how could we get that one? That's a fun one. 42, if we do, remember that with this, we're going to remember that rule of 3 and 10. So 0 to 1, that's our baseline, but then we've got 3 is twice the power, and 10 is 10 times the power. Okay, so that's our decibels side. Here is our watts side. Okay, measured to the milliwatt there. So if we take a look at this, what we could see is that, how could I come up with 42 as an aggregation of 3s and 10s? That's really what it boils down to. How about this? 3 plus 3 plus 3 plus 3 is 12, plus 10 plus 10 plus 10 is 42. Okay. And so then we need to convert that back. So what that means is for every 3, remember that becomes a 2 in terms of power strength. So we're doubling the power each time we add 3 decibels. So 2 times 2 times 2 times 2 times 10 times 10 times 10. So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 10 is 160. Times 10 is 1,600, times 10 is 16,000 milliwatts, or 16 watts. Now again, if you were to use the logarithmic approach to this, you'd find out that it's actually very specifically about 15.8. So again, remember that this rule of 3 and 10 gets you roughly to the right number of milliwatts, but it is not exact. It is there's a bit of rounding to get to those numbers, but gives you the rough idea of the wattage that we're working with as we're pushing out this signal. Again, our EIRP, transmission power, antenna gain, and loss.